Hi there folks, another lovely day, although it's a little bit chilly round the front of back of my house. Actually. Right, we're going to have a look at MaCaulay's method, and this is when you look at a beam, you want to find the slope or deflection or the slope at any point in the beam. You can use this method to create an equation that means that you can plug in any value or any part of the length and you'll be able to find the deflection or slope at any part of the length. Right, so we're going to have a quick look at that. What I want you to think about is, when you think about differentiation, that gives you the rate of change of the delta y over the delta of x. The change in y over the change in x will give you the gradient or the slope. So bear that in mind when we look at this. Right, I want us to think about Young's modulus and the second moment of area. And Young's modulus is a ratio of the stress divided by the strain. Right, now if you think about this, the smaller the strain is going to be, the bigger Young's modulus is going to be. And what does a smaller strain mean? Well, that means there'll be less elongation, less stretching, or less compression depending on the stress. Right? Now what that means that then the beam is not going to stretch as much. So in other words, the stronger or the bigger Young's modulus is, it's stiffer because there's less stretching. And that, coupled with the second moment of area, which is its resistance to bending, coupled with the material's kind of resistance to bending. So this EI, that's its stiffness. Right. Now, if you have the total bending force, and that's divided by the stiffness, that tells you how that bending force is going to affect the beam with a Young's modulus of E of that and the shape that's going to give it its stiffness. I hope you can kind of see that. Right, so and remember when we're talking about the beam bending, what we have is the slope and we have the deflection. So this slope here is the ratio of the change in y and the change in x. So that will give us the slope of the beam at any point. If we find dy, and this is the same as dy by dx. It's the same thing, virtually. And this means that if we can find y, obviously we'll get the distance it has moved from the horizontal axis. And if we differentiate that, we will get the slope. And we're using MaCaulay's method, we can work out the slope and deflection at any point along this beam. Right, and a common expression you'll see is EI, the stiffness, times the second derivative of y equals the bending moment. So if we move this across to here, we'll be left with d2y by dx squared and we take this out because this is a common factor, or a constant. The only thing that's going to change is this and this. So 1 over times moment, and then what we'll do is, let's see, what we do is we'll integrate. Oops, wait a second. Right, and what that will do is that will give us dy by dx equals 1 over this integral, and then if we want to find y again, we'll just integrate this again, and that will give us y. Something like that. But what I'm going to do, so basically what we do is we just use this expression. Where was it? We use the d2y by dx squared equals 1 over e times the moment. What we do is we find the moment from a certain point on the beam, and then we just simply integrate it twice. So all we're doing is integrating this part, and it's very simple integration. What I'm going to do is I'm going to draw out a wee example, and we'll do that just now. Right, I hope you can see that there. We've got a beam that's 9 metres long. At 2 metres we have a 210 kilonewton point force. At 125 we have at 6 metres we've got a 125 kilonewtons, and right along the beam we've got a UDL at 26 kilonewtons per metre. Right, first thing we do is find out the total. We want to find out the reactions at YA and YB. So we'll call this, in fact, wait a second. I'll put that like that. It's AY and BY. That's just to indicate it's in the vertical plane. Right, so AY plus AB equals 569 kilonewtons. If we take moments about B, say, remember I'm always clockwise is positive, anti-clockwise is negative. That equals 0, which will equal, y times, that's going to be 9 metres, and that's positive, so that's going to be pushing that round the way. So this force times 9 metres is pushing that round that way, minus the 210 at 7 metres, minus the 125 at 3 metres, and then we'll have this here is 26 times 9, which works out at, so that's 234 is, you treat that, you take the complete force of that and treat that like a point force, which is going to be 4.5 metres, and that's 26 times 9 is 2, 3, 4. Oops, 2, 3, 4. And that all comes out at y equals 322 kilonewtons, and when you put that back into this equation, by, oops, equals 247. So we can say 247, and here is 322, that is 322. Hope you can see that. So I just found the vertical forces and took the moments, and we've worked out what these forces are, the reactions are. Right, it's a bit clearer there. 322 and 247. Right, we go on to the next bit. Right, so we've got your beam here, 2 metres, 4 metres and 3 metres. That's right, that's 9 metres altogether. 210 kilonewtons, 125 kilonewtons, and obviously we've got our UDL on here. What's that? 26 metre kilonewtons. Right, so what we do here is we take a point and we take a slice out of this, right about there, and what we do is we take moments around this section and then we'll integrate it, and that'll give us a slope. Okay, right, so we're gonna, there's a beam there, the length x, that's the 9 metres total distance from there to there. We're going to take a wee section here, and this is going to be distance x from the left hand side. So let's look at the moments here. There's going to be this reaction here times this distance x. And that's positive because it's bending it round in this direction. This one here is going to be negative. And that distance from x is going to be x minus this 2 metres. So that's x minus 2. And we'll look at this one next. That's 1, 2, that's 6 metres. So the moment here is going to be 1, 2, 5 times x minus 6. Now, this bit's a bit more tricky, as we're trying to find the midpoint with the UDL, and it's only the midpoint, it's not from 9 metres, it's from this point, it's the middle of x. So the actual distance here is x over 2, because we're halfway, because remember our UDL, you treat it as a point load halfway along. So this x, halfway along, that's going to be x over 2. Now we're going to have to multiply that. Now how do we do that then? Well, the thing is, this 26 kilonewtons per metre, you can actually say, well, this distance here is going to be x, and it's 26 kilonewtons per metre. So you can say then that the weight along this length is going to be 26 times x, and remember the x is so many metres. So we're doing the same thing. What we're doing is we're saying, right, that's not 9, but this length is x, so it's not going to be quite 2, 3, 4, because we're taking a little bit out of it, but we're not sure what x is. X is just an arbitrary distance we're using, because when we figure this out we can use any value of x. So if halfway along there is x over 2, and then the actual point load is going to be composed of 26 times the length, which is x. I hope you can see that. So what that's going to work out at is, let's see, 322x, that's 322, minus 210, we'll leave this like this just now, minus 125 times x minus 6, and this is going to look like 26x squared over 2, or I'll just write that as, oops, 13x squared. Oh, can you see that? Right, can you see that? Good stuff. So, if we integrate a moment. This is a constant here, so we'll just be integrating this part. And this part here is 13 squared over 2. And let's face it, that's a complete doddle compared to what you've been doing in maths 4, 3 and 4 and stuff. So that's going to be 3 2x squared over 2 minus 210 x minus 2 squared over 2 minus 125 x minus 6 squared over 2, and this is minus 13, and that will be x to the, well that's just 13, I took that 2 out, so that will just be 13 times x cubed over 3 plus c1. That's our constant of integration. What was I going to say about that? And what we see is a way of looking at this to try and explain boundary kind of conditions. If you, I know you've all done dynamics and things, so if you imagine you've got an acceleration time graph, right? And you say we've got acceleration, right? We know if we integrate acceleration, we're going to get the velocity. So if I integrate this to time, what I'll get is acceleration times time plus a constant. Right? Now, we all know that the velocity equals u plus at, and that's what that is. And so this constant here, or this constant, what is that? We know that's the initial velocity. So what this does is it brings in a kind of starting condition, and that's what this is here, or this is here. And so if you were going to, if this was 0, you'd be starting at the origin. Or if this you integrate this and you work this out to be, say, 10 or something, and this would be velocity, that would be your starting point. Or if you were going backwards and you suddenly started going the other way, accelerating the other way, your starting point initial velocity would have been minus 10. Just to give you an idea of where these are coming from and what they mean. Right, so we're left with this equation. I've just divided through with the 2's here. I've left that like that. Didn't want it to get too ugly. We'll call this equation 1. Right, next thing we're going to do is integrate it again. I mean, this is our slope, but because we've got this c there and we don't know what that is yet, we can't figure the slope out yet. Right, so let's do that then. Yeah. This will be, let's have a look, see. If I integrate all this again, and we'll end up, integrate this, we'll end up with y, which is the deflection. And let's do this then. That's going to be 161x cubed over 3 plus c1x plus, again, another constant of integration. Right, and you have to bear in mind that this is like the positive bending moment, and these are all just kind of getting subtracted away from it, and that's why this is the kind of initial conditions, so therefore these don't have constants. Anyway, this is going to be minus 1, what's it? X, what am I doing here? Yeah, wait a second. 105 over 3, so that'll be x minus 2 to the power of 3, and minus 62.5, again that's 3, x minus 6 to 3, and this one here is going to be 13 x to the 4 over 3 times 4 is 12. Hope you can see that. And we'll call this equation 2. Right, we're going to apply boundary conditions here. If you remember that at the ends of this beam from 0 to 9 metres, when x equals 0 and x equals 9, there's going to be no deflection at these points. So x equals 0, y is going to equal 0, and when x equals 9, y is going to equal 9. So if we apply these boundary conditions, we only need to look at this first part here. You can see that that's going to be 0, that's going to be 0, that's going to be 0, and C2 is going to be the only thing left there, which, if you look at this, it's going to equal 0. So C2 equals 0, which is handy. The next thing we want to do is apply the second kind of boundary condition, this one. So in other words, we're going to plug 9 into all this, and we know that's going to be 0, so that, and we'll be able to figure out C1 from this. Right, so this is going to be 0, and this is plugging this into equation 2 again here. So 0 is going to equal 3, 2, 2. No, wait a second. That was 161 I've got there, obviously. So that's 161 over 3 times 9 cubed, which equals C1 times 9. Oops, that doesn't equal that. Apologise. Yeah, that's a plus, right? Plus 0, or C2, minus, see, that's it's a positive bend the moment. This is all the negative, or anti-clockwise moments coming in now. So it's minus 105 over 3, that's 9 minus 2 cubed, minus 62.5 over 3, 9 minus 6 cubed. That's that part, you can see that, and then minus 13 over 12, and that's 9 to the power of 4. Right, and when we work all that out, let's see, right, that works out at C1 equals minus 2160.86. Now we just plug that back into the equation. Right, so you put that in equation 1, gives you your slope, just plug that into there, and that will give you the slope at any point of x along your beam, and do the same again for your deflection. What was that again? Let's see. Right, and when you plug it into the deflection equation, it kind of looks like that. I've put brackets around these because in the first one, this implied that I was actually multiplying this first bracket by that. So I've put these big square brackets around to show you you're multiplying the whole thing by it. And that's basically MaCaulay's method of finding slope and deflection for a given beam with various loads of sorts on it. Again, what I'm going to do, that was one wee example there. I'm going to send you a tutorial. Right, I'm going to yeah, that's just a quick example there. I'm going to send you a tutorial on a few examples of this, and then what I'll do is I'll go through the tutorials in a video to help you with that. Hey, I think that's it actually. Right, take it easy. Thanks for listening.